Welcome to the SB Grid YouTube channel. Software tutorials by developers, lectures by structural biologists, unique content brought to you by SB Grid.
Welcome to the February edition of the SB Grid webinar series. Just some procedural stuff before we get going. So the next webinar is March 12th. That's going to be Shores Shearis, who I apologize for butchering the pronunciation of his name, which I should know better. And he's going to be talking about new thing for the Relion. Most folks are probably aware that there's a new Relion beta out. And if you have questions as we go along, then feel free to either use the Q&A or send them to one of the hosts in the chat. And with that, today we've got Bjorn Forsberg, who's here to talk to us about Occupy. And with that, thank you for joining us, and I'll turn it over to you. And thank you for bearing with us through the troubleshooting and the reconnects.
Absolutely. I should begin by apologizing if my voice is a bit strained. I just came out of a 6-day flu window, so I'm trying to recuperate, and I apologize if I sound a bit coarse. But yes, today I'll talk and describe Occupy a bit, which is a software tool that I wrote together with Pranav Shah and Alistair Burt when I was a postdoc at Oxford University. And it's a fairly simple software tool to do some tentative heterogeneity and occupancy analysis of reconstructions that come from cryo-EM analysis. So the fundamental issue that we try to deal with in cryo-EM analysis is one of compositional heterogeneity, where we try to separate things. So if we have particles that are constituent of protein A and some of them are bound to B, for say, then any sort of, if we don't disentangle this completely, then we will see some sort of inherent average between the two. And this will manifest as some sort of contrast loss in the B component. So the average of different types of particles will sort of manifest differences from both of them. So conventionally, what we try to do is to disentangle these through classification or other processing pipelines. But there's a number of limitations to this procedure. If you have very many components, very quickly you run into issues stemming from just the complexity of having all of the different combinations. This is especially easy to envision if you have something highly symmetrical like a virus, where you have spike proteins like this one. Obviously, we can't find all of the virus particles that have the spike proteins in a certain configuration. Instead, you would want to be able to disentangle these and look at individual spike proteins, but that might be very difficult as well. So just being able to detect the inherent heterogeneity within the consensus reconstruction is really important. And this becomes even more pronounced when you have other asymmetric reconstructions that have massive levels of compositional complexity. It might also be that the component that you're interested in looking at is too small to identify through these conventional pipelines. Again, we're zooming in on the spike of a viral capsid here. And there is a component that is simply too small to be recognized. Within each individual particle image that you would like to process, the noise is so high that you can't be confident about whether or not something is there or isn't. But from the consensus reconstruction, we get a lot of noise cancellation. And from that, we are able to extract some statistical properties of that region and sort of confidently say something about the average that can inform us about the distribution of particles from the beginning. Also, if we try to use classification and these kind of conventional processing pipelines to be quantitative, we quickly run into some fundamental issues. In classifying this A plus B, for instance, we might find a class with 30% of the data that has A. We might find a class that's 10% of the data that is clearly A and B, fully occupied. But a large proportion of the data might exist in a class which is more ambiguous. And without some method of quantifying B within that mixture, we have enormous error bars for the distribution of A versus A and B. So that, coupled with the sort of stochastic variation that you see from run to run, here, for instance, again, looking at this viral capsid protein, we have very good established alignments, and we know exactly what we're looking for. And even so, the variability between different runs is enormous. So in this first run, in the first class, you see the viral spike, and you see some remnant of it in the other classes. In run 2, you see no class being predisposed to classify this one spike. And in the third run, the first class actually shows what I would call a very good class. But nevertheless, the second class is 80%, and there's some indication of a spike there. So how many particles are we missing? We don't know. So this is basically the problem set Occupy tries to deal with, to look at the consensus reconstruction instead of relying on pseudo-quantitative processing pipelines. So this is basically a slice through a reconstruction that shows some compositional heterogeneity. And when you and I and experienced structural biologists, when we look at this, we sort of understand what's happening. And the notion is to transfer this intuition over to a program that can be quantitative about it. So what we're going to do is we're going to, for every point within this reconstruction, do some statistical analysis within every small region, and then establish a measure of contrast. That measure of contrast is going to be a proxy for the heterogeneity that we assume is within that region. Part of that means assuming that flexibility is negligible. And that is a very big assumption, and one that I will address down the line. But the basic assumption here is that we don't have any flexibility, and that any contrast attenuation or sort of loss of contrast is due to compositional heterogeneity. And then from those assumptions, we can then work backwards to sort of deal with flexibility, but that's the fundamental assumption. So imagine then that we do this procedure. We estimate for each point within this reconstruction a measure of contrast. Now, in a very, very simple way, we can think of this in this way. So on the left, you see a number of pixels where we have estimated the level of contrast. And there's a region where we've found that the contrast is 5. And then there's a region where we've estimated that the contrast is 2, and then a region where it's 1. Intuitively, this agrees with the notion that we have a big region where the occupancy is 100% because we have a lot of images with something present in that region. We have good noise cancellation, high contrast. In the region where we only see a contrast of 2, we can assume that there is only partial contributions from a consistently averaging object. That is, a lot of the stuff that went into the reconstruction at that point was just noise or empty. So this really maps to the image we see on the right, where we have a large region with 100% occupancy, one with 40 and one with 20, which is in correspondence to the level of contrast we see. So the mathematical simplicity behind getting from the contrast level to the occupancy in this case was just to divide through all of the values by the maximum value. And this is a very naive way of mapping all of the estimated contrast values to the 0-1 range, where we can interpret 0 to 1 as 0 to 100%, right? So where we see the highest contrast, that would be 100% occupancy regions, and then gradually fall off down to 0% occupancy, where we have complete loss of contrast. However, as soon as we have any level of noise, this very naive procedure runs into fundamental issues. Notably, if we divide through by the maximum value, then of course we will systematically underestimate. And you can see this in this instance. I've sort of overlaid the regions that we saw just in the previous slide, just for simplicity. But you can see now that since we have this value 7 there, that means that if we use that value 7 to divide through and normalize in this manner, we're going to end up with what we see on the right, which is basically one region having 100% occupancy and all other regions having less than 100% occupancy. And we know that this is unintuitive to begin with, because protein doesn't behave like this. Our reconstructions tend to have fairly substantial objects that have predominant, that are sort of coherent. And then, so we would expect larger regions than a single pixel, for instance, to be 100% occupant. So in order to fix this in the simplest way possible, what we can do is avoid the systematic underestimation. And what we do to normalize is we, instead of dividing through by the maximum value, we divide through by a value x. And then we find a systematic procedure of determining what that value should be, such that we don't get any systematic error. So effectively, what we will be doing is finding a procedure to divide by a smaller than the max value, and then clipping everything that's then a higher than 100% to 100%. So this is a very naive way of reducing the systematic error and getting something that looks a lot more reasonable. It's an approximation, but it is one that works extremely well. So here's an example of that. So if we, instead of dividing through by 7, still use this sort of noise containing field, and we divide through by 5, which is the theoretical true value here. And then we can see that on the right, we see a much broader region defined at 100%, which constitutes the bulk region. And then the other regions show less systematic error. They are not as underestimated as they would be otherwise. There is, of course, still error within each individual point. That's not to say that that's not happening, but we are avoiding the systematic error in normalization, which is the fundamental thing that Occupy does. So the algorithmic procedure to do this is basically to say that we're just going to ignore the high values. And then in order to determine which high values to ignore, we use a percentile filter. And then we choose that percentile to be optimal with respect to minimizing the probability of both under and overestimating the local scale, or the local nominal value. So that percentile is derived based on finite statistics. So basically, when you give the input reconstruction, you determine some sort of granularity for your search, how detailed your search should be. And that determines the size of the region around each point where you want to probe. And based on how big that region is and how many pixels there's in it, Occupy then derives a percentile to use. This sort of roundabout way of doing it allows you to just change what the kernel is, what the granularity of the search is, and any normalization factor, and then the program will adapt to it in a very simple and robust way. So when you open the Occupy GUI, you will have these fundamental input parameters. You'll give it the input map, and then there will be a low-pass filter that you can provide. And then the kernel parameters will be suggested to you based on that. And then if you want to change them, you can. And the tau percentile will be recommended to you. This is something that you can change, but it is recommended to you in a systematic way. So what you will end up with is one of these pseudo-spherical kernels that you see in the central panel. And then the percentile value will be basically set according to that. And you can adjust it if you want to, but I wouldn't suggest doing it unless you have a very good reason to. So that's sort of talking about under the hood, what goes into estimating these local properties. But fundamentally, you can think of it in a much simpler way. So you can keep this sort of picture in mind, where you have the reconstruction on the left. The local contrast value maps in some, you will get a local contrast estimation for each point within that map. And then Occupy will then suitably normalize that to be maximally useful to you. And this manifests as the local scale. So you can see the correspondence between these two, and it sort of maps to our intuition about what is happening in this picture. Where we see loss of contrast, we infer that the averaging procedure has not been high fidelity, basically. So there has been variability within the input data, and that's what's manifesting here. So the local scale is, to a degree, showing you the level of variation within the data as it contributed to each point in the reconstruction. And if you wanted a simple way of thinking about how this maps, you can think about the image histogram as well, which is the kind of histogram that you see when you open these reconstructions in, for instance, Chimera, that many of us are using. So you usually have a spike around 0, which is due to the fact that we tend to do background normalization, so that we have a 0 mean background. That sort of pushes most of the volume of the map to be around the 0 mean and have a noise distribution there. And then any higher values that is right shifted or to the right of this central peak, those represent contrast. And the further to the right you are, the higher the contrast is. So you can intuitively map the estimated occupancy that, or local scale that Occupy calculates to this range. And again, we don't want to divide through by the rightmost element, but Occupy really systematically is all about finding the best point where you define 100% occupancy. So that's a much more intuitive way to think about what's happening if you don't want to deal with all these kernels and everything. But there is one more parameter that is extremely useful to consider, and that is the tile size. So it's the last of these fundamental scale kernel settings. The tile size really deals with the fact that you may have very highly scattering objects in your reconstruction. Sometimes you have a high resolution reconstruction, such as this Apoferton reconstruction, where the resolution is sufficiently high that a single high mass atom shows much higher reconstruction values. If you don't consider this at all, Occupy would find that this one location with this high mass atom has 100% occupancy and everything else will be underestimated. So this tile size really allows you to define the granularity of what 100% occupancy should be. So in the conventional here is, conventionally we say 12 pixels, but this should really be dependent on size. So around 15 to 20 angstroms is typically the size of protein components, right? So secondary structure elements. So if you define that kind of size, then anything smaller will not be allowed to dominate the estimate. So as you can see here, if we just set it to sort of the tile size to 12 cubic voxels, it will calculate this over 20 by 20 by 20 tiles, and then you will have a normalization that sort of doesn't allow very small things to dominate your estimate. So you won't end up with a systematic underestimation due to low mass objects. And this is really crucial if you have, for instance, iron sulfur clusters or high mass atoms or ions, magnesiums, this kind of thing that dominates the scattering profile in your map. Yes, and so to deal a bit with flexibility, the naive approach that we took in Occupy now for the first incarnation is to simply reduce the influence of variable contrast due to flexibility. So what happens when you have flexibilities that you have local variations in resolution? So if we employ a low-pass filter before we estimate the local scale, then we will end up with something that we denote occupancy mode local scale. We don't call it occupancy because we are still under the influence of flexibility. So it's not precise, but it does aid in removing differential resolution due to flexibility. Sorry. So if you are interested specifically in compositional heterogeneity and you want it to be as close as possible to the true definition of occupancy, then it is a good idea to play a bit with using different low-pass filters when you use this occupancy mode local scale. Okay, so now to be a bit more pragmatic, the fundamental input-output of Occupy is that you just provided a reconstruction. It does not know what a PDB file is, so it cannot provide you an output file where atoms are labeled by an occupancy. It estimates the point, it estimates the compositional heterogeneity of each point in the reconstruction. So what you will get is a new reconstruction output, which basically labels or colors the input. You can use it in many different ways, but fundamentally it is an annotation of your input reconstruction. There's a few different optional outputs that you can use Occupy to generate. So you can modify the input reconstruction, right? So you can modify it according to local scale. You can also remove solvent noise because it does inherently an estimation of each point in the reconstruction of whether or not that's noise or background or whether or not it's content. You can also choose to histogram match your input and your histogram match your modified output to your input if you want maximal correspondence between the two. But you can also do very neat things. You can generate a subtraction mask. So if you find a modification that sort of really attenuates away things you don't want, it's straightforward to use that to generate a subtraction mask that you can use in your processing pipeline. You can also define solvent masks by just thresholding the local scale directly in the GUI. And you can also estimate the local scale or occupancy within a predefined mask that you choose and provide to the GUI. So I am hoping that I can show you a few of these things. So I'm going to see if I can. Hopefully this works. I hope somebody shouts if it does not. So this is the Occupy GUI. And what I'm going to start by doing is just fetching an EMDB entry, which is the gamma secretase. So this is now a view of the folder where we are processing as well. So just to show you that this map is now fetched from the EMDB. Once I started fetching, it also started to log this, and there's a text file here, which is basically just logging everything that happens. This is a target mask that I will use in a bit. So again, here is now the Occupy GUI. You can basically just view your reconstruction a bit to make sure that it is what you expect it to be. If you now hit estimate scale, it will estimate the local scale. It will do so fairly quickly. So again, we chose the processing modes for this because they are extremely quick. So what we can do is we can visualize the local scale here. So you can see this is a membrane protein, and to some extent we see that the detergent belt is lower occupancy. This is a mode of flexibility, in fact, but nevertheless. So if we say occupancy mode and estimate that scale instead, we will now have a bit of a nicer estimate because we've now employed this low pass filtration before we did the estimation as well. So here you can really see sort of the difference between how detergent is perceived in terms of local contrast to the protein. And what we can also see is that here is now the solvent model, which you can have a look at as well. This is now the fit basically to the noise profile, and anything outside of this is now interpreted as content. You can see that if you have a glance at the confidence estimate as well. So the black regions here are basically interpreted as being solvent in this case. Yes, what else can we do? We can, of course, now modify this as well. So if we wanted to amplify, basically what that is going to do is it's going to look at every region that was estimated to have partial occupancy, and it's going to inflate those or amplify them. So if we increase the power here, what you're going to see is that it starts to boost the low occupancy components. We can do the converse. We can attenuate them away, and effectively what we're doing in that case is we're removing detergent because detergent was here perceived as being low occupancy. If you want to have a bit of a more sort of intuitive view on that, there's a plot option as well, which will map the input scale to an output scale. So if I increase this attenuation, effectively what I'm saying is that anything that was estimated at 60% occupancy is going to get mapped to have a new 0% occupancy. So effectively what I'm doing, if I look at the preview, is I'm removing everything that is low occupancy. Let's reduce that a bit just for visuals. And then let's reduce the amplification as well. And then there's a combination of the two called sigmoid, which basically has a power to say how much you should affect, but also gives you a bit finer control over which point is interesting to you. So if we look at the preview, we can see here that if I move the pivot up, then I start to attenuate away higher and higher occupancies. And then the power is corresponds exactly to how much I want to change that. So this is just a preview, but we can affect all of these changes by just clicking Modify Map. If we check the output log, so we're generating a bunch of new files here, and it's done. If we want to have a look, we can just launch Chimera. So this basically creates a startup script for Chimera that it can then use to open. So this is the input reconstruction, and it is at this point just colored according to the estimated local scale. So if we look at the amplified version, this has now basically amplified all of these low occupancy post-translational modifications, which in this case is glycosylations on the surface of this membrane protein. You can see that it's also boosted the membrane because the membrane is perceived to be low occupancy. Again, a membrane is a bit special. It's a form of flexibility that we have quite a difficult time to deal with. We know how to do it now, but for this incarnation of the program, it actually turns out to be a bit useful because if we look at the attenuated reconstruction, we basically removed the detergent. So this is a very handy tool to just sort of remove the detergent completely. And you can see that even if I go to really low threshold values, the detergent is effectively missing because we have a very good way of estimating what the contrast is, what the intensity is, and exactly what we need to do in order to change that in the correct way. The sigmoid modification tends also to be very useful for this, especially in membrane proteins, because you can effectively determine exactly what components need to be boosted and attenuated. So those are the modifications. Let's see what else. Yes, of course. So let's actually launch this again to have a quick look. No, we're going to start with the subtraction mask. Sorry. So if we wanted to let's now say that we were happy with the sigmoid modification and we would like to subtract detergent from all of the particles that went into this reconstruction, such that when we then reconstruct it, the detergent isn't there. So we want to do that. What we need for that is a subtraction mask to provide to either CryoSpark or Reliant or any other program that's capable of doing it. So in that case, what we can do is we can simply leave the sigmoid modification active, and then we just say generate a subtraction mask. So you will see that the output here is made a subtraction mask. And if we now open Chimera here, if we now open this subtraction mask, let's see, subtraction mask sigmoid, yes. You will find that it's basically a non-binary mask. So it's a soft mask, and it has basically dictated what parts of the reconstruction should be kept intact and to what extent. So any components that need to be subtracted will sort of come in at the level where they need to be subtracted. So this is a very robust way of making sure that you come up with reasonable subtraction masks without having to define every single region. And you don't have to sort of fiddle around with the ellipses and Chimera and sort of do subtractions and minus and all these kind of things, these ad hoc modifications. This is a tool for you to be able to generate those subtraction masks by saying we took the reconstruction, gave it to Occupy with these settings, generate the subtraction mask, and then use that. And that is reproducible given the version number, right? So that is a very useful use of Occupy. But then let me also show you this target mask feature. So the target mask is basically asking about, when you provide a target mask, you are asking about the occupancy or the compositional heterogeneity within that small region. So again, let's have a look here. So we have the, for instance, this sigmoid modified reconstruction. And let's open the target mask that I have prepared. Let's see. We will make it easy to see. So basically, what we are doing is we are simply asking the question within this small region, what is the occupancy? Because we can see that there's something here that we might be interested in. So if we then go back to Occupy, and then we ask, here's the target mask. And then we say estimate scale. Now it will provide that answer here, right? So it says targeted occupancy estimated at 0.55. So according to this, the procedures within Occupy, it has estimated that there are 194 pixels within this target mask. A reasonable tau value for that number of pixels is 98. And that the occupancy within that region is about 55%, which sort of makes sense with respect to seeing some partial component there. So those are a few fundamental ways you can use Occupy in order to be a bit more quantitative. There's more features to sort of recalibrate the noise level and stuff like this, but those are covered in detailed tutorials in the online documentation. Yes, so a further note about this modification procedure, because I think that is one of the more interesting aspects of this. You can see that whereas when we use Occupy to estimate the local compositional heterogeneity and use these modifications, it gives us a picture of the level of variability that we can expect within our data set as well. So the original reconstruction has some variation, but when we've amplified, we've effectively said, okay, so some of these particles have all of these constituents, and this is what that would look like. Some of them don't have all of these constituents, and if we take away the lowest occupancy components, this is what it would look like. And on the far right, you see somewhere in between. So this is giving you some sort of idea of the different molecular species or complex species that exists within the dataset, simply from the fact that you have variability in some regions within your reconstruction. So this is not to say that these are the only things that exist in your dataset, but it is giving us some sort of clue just from the reconstruction alone, what level of variability there is within the data. With respect to how small you can look at this and how good the results are, we did some validations against synthetic data. So in this case, basically, we generated synthetic densities. We took a dimer from the PDB, and one of the protein chains, chain A, we modulated the occupancy of it and generated densities as they would appear. And then we asked Occupy to sort of estimate the compositional heterogeneity, and then we checked whether or not those were in agreement. So what we found was a remarkably good agreement, fairly robust to input settings. What we do see is that this occupancy mode, which is basically affecting a low-pass filter, that introduces correlation in the pixels such that this tau value is somewhat too high. If we reduce it optimally, because we know the ground truth here, then we can get an even better estimate. So we have a bit of work left to do in order to make sure that we don't input a too high tau value, basically, when we employ this local the occupancy mode, local scale. But then again, we already know a better methods of doing this. So I think rather than adjusting this tau value, we're just going to move on with some other methods to estimate this more robustly. But even these simple procedures show one thing very clearly, and that is when you are doing this kind of spatial analysis, when you're asking questions about the statistics within very small regions in real space, there's a tremendous amount of information. You can use Occupy with extremely small kernel sizes, and the estimates don't suffer for it any more than they would if it was bigger. So even kernel sizes as small as you see on the far right here, where you don't have that many pixels, you get very good significance. Even as NAD cofactor within one of these synthetic generated densities that we validated Occupy against, you see very clear distinguishing features for the low occupancy component. It's correctly estimated. You can put it back using the modification and it looks reasonable. When you look at high resolution reconstructions from real data, you see features that, even though they are probably in part stemming from flexibility, are very interesting and that I had never seen using any other tool for analysis. So for instance, here, the differences in the ordering of surface loops on the apoferritin is reflected by local scale. So we see contrast loss. We don't immediately attribute this to sort of loss of resolution because the resolution is homogeneous, but using this very, very fine-grained tool, we can look at a very few pixels, a very small region, and find good relevance and significance in features that stem from partial ordering and stuff like this. So this very detailed, small spatial analysis based on real space statistical properties of these maps is something that's only going to get more and more used. And I think this is a fantastic example of that. If you look at really high resolution reconstructions, as I said before, you can sort of identify or see variations between individual atoms, because an atom is represented by more than one pixel, right? So just a few pixels is enough, really. And when we look at sort of connecting back to this viral capsid, this is a reconstruction from a symmetry expanded and partially subtracted locus on one of these viral capsids. And not only can we sort of identify what the viral capsid occupancy or a viral spike occupancy is, even smaller regions we can identify. The program correctly identifies that we've sort of incorrectly subtracted most of the capsid. So it's giving us a very rich view of something without having to use Fourier space analysis. So just to sort of conclude and give a bit of an outlook for what this is and what it will be, is that at the moment it is a very useful tool to analyze and look at local differences within a map. It can help you quantify and permit some level of hypothesis testing where you can compare between different data sets and reconstructions exactly what's going on. It increases the reproducibility because you can just use the program and refer to it and the settings that you've used with it, and people will know what you have done and they can reproduce it. Hopefully it will start to help how we process data now to just some level of heterogeneity estimation that isn't based on counting particles in different classes and sort of circling different groups of particles within phase diagrams. Hopefully it can augment current clustering by allowing this map modification to direct class convergence a bit. And automasking is something that's always controversial, whether or not it will be possible, but this is to a degree a fairly robust way of doing some level of automasking that could be employed in these processing pipelines that we're using currently. And hopefully in the future, this will help us to sort of make the programs more intelligent and look for these things specifically, right? So if we have programs that are meant to understand compositional and conformational heterogeneity, these kinds of estimates and sort of metrics for specific properties that we expect proteins and complexes, biological complexes to have, that will only allow the programs to do more intuitive things and sort of tell us things more directly. So hopefully we're working towards that as well. And with that, thank you so much for listening to my flu-ridden rant. And thank you to the people who helped build this and all of the funding agencies, of course, that allow me to sort of dedicate my time to this kind of endeavor. I will happily take questions.
Well, thank you for a great talk, especially when you were in the midst of recovering from flu. So I didn't think it impacted things in any way, and didn't want to interrupt you and tell you that your desktop demo, everything was visible. So that was all great. So if there are questions from the audience, feel free. You can either use the Q&A section, you can raise your hand, you can send questions in chat. And we have a hand up. So Chin Lee, you should be able to unmute yourself.
Yes.
All right.
Great talk. Very interesting software. I'm excited to use it. So for quick question is, for identify the ligand occupancy, do you have to generate a target map, or you can just go to look at a map and it give you the value from the PDB file? Or
so I would, if you want to use the target mask feature, then basically you have to generate somehow generate a mask to cover your region of interest, right? And then it will treat that region of interest as a region. Normally it sort of does a spherical volume around each region, but now it has a custom region that you are asking about, right? So I think the reasonable way of doing that is either do like what I did, some sort of general volume around it. It doesn't matter if there's sort of void included in it. It's fairly robust to that. But otherwise, if you have like a PDB file that aligns with your reconstruction, it's probably easiest to sort of isolate some sort of molecular component with the right shape and position, and then basically mold map that or sort of adjust it. There is a bit of tinkering there, yes.
Yeah. So, for example, one of my protein has FAD, which is kind of long, elongated, have different shape. So how do you generate a map for that? You isolate that map, the molecule, and generate a map and apply it to the occupy.
Yeah, I think you can't generate you wouldn't use occupy to generate the target mask. That is something that I think if you play around in Chimera, it's fairly straightforward. I think you'll find many people have recipes to do this specifically. It's a matter of a few commands to sort of generate some sort of volume that looks like your molecule.
I see. Thank you.
One other question. Could you say a little bit more about kernel size versus kernel radius versus tile size, and like how those interrelate, and how do people pick them, or how should people pick them?
Yeah. How should people pick them? Depending on the characteristics of your reconstruction, your voxel size, your resolution, the level of flexibility, the type of noise, it can affect how good or reliable your estimate looks. I know it's such a bad thing for me to sit and say that once you look at the estimate, you will understand whether or not it did the right thing or not. This is not something I want to say as a software developer. But to an extent,
sometimes things are empirical, and that is
unfortunately, yes. And we're still in this sort of this is why we've opted to do it in such a way where you are able to adjust these parameters and inspect the output, and then the program does its best to remain rigorous and sort of do it systematically. But it is subject to some experimentation. Increasing the fundamental kernel settings mostly just tunes the size of the region and the shape of it. That's it. And then the tile size, as I mentioned, is something that sort of dictates your normalization volume size or so. This is actually covered in tutorials in the online documentation as well. So if you're curious, most of it is going to be in there saying like, okay, so if you're seeing this, try to adjust that and then adjust this and so on and so forth. But there is some experimentation involved. Yes.
Thank you. And another question, can you see waters in the higher resolution maps?
So the higher res, obviously Occupy doesn't find anything that isn't already there. This is about quantifying the level of contrast within a map, right? So the question, I guess, is rather, is it able to distinguish variations in contrast on the level of, or on the size of water molecules in high resolution maps? And I would say yes. To the degree that you are able to sort of assess that the waters are sort of there to the same extent, the differences between different water molecules and their occupancy as estimated by the local scale seem to be legitimate.
Thank you. We have a question from Wei Zhang, which I think you addressed, but so in the context of ligands, is there a way to differentiate occupancy of the ligand versus flexibility of the ligand with the contrast gradients, or is that still in progress?
So it is a work in progress, dealing with flexibility, but I think we have better metrics now. So we used this max value filter as a very fundamental, simple, fast filter in order to quickly determine the local statistics in each individual region, right? We have better ones now that are able to simultaneously distinguish between the two. So we can actually recognize if loss of contrast in any given region is due to compositional heterogeneity or blurring, right? And blurring is the fundamental aspect of anything that has to do with flexibility or otherwise, right? So we can distinguish between blur-induced contrast attenuation and non-blur induced contrast attenuation. So soon we will be able to do that. But in terms of ligands and flexibility, we're also talking about alternate conformations, right? So if you have a ligand that is in two different poses in the same binding pocket, that's going to be inherently difficult. You're going to need very high resolution in order to do that. And I think at that point, you're at the resolution where there's better tools to do this quantifiably.
And the more variables you throw in, the harder your combinatorial problems get.
Yes.
So. For the amplify functionality, so switching topics completely, or not completely. It seems like that's at least intuitively similar to map sharpening, but I mean the functionality is different. But if you're looking at it from, show me something in my map, is that a fake similarity or an illusion similarity, or? That question, I apologize. My question was not too fully coherent.
No, I get the question. I get the question, absolutely. So there is a fundamental difference in the sense that we are not affecting any sharpening when we're doing amplification. Effectively, what we're doing is we're increasing the mass of a local region. We're not actually making it more distinguished. Sometimes it's easier to sort of visualize at a given threshold or so. But the analogy to think about is if you consider some feature defined by a Gaussian, sharpening would be basically squeezing that Gaussian, whereas all we're doing is making it fundamentally have more mass. So we're just heightening it, right? We're not squeezing it at all. So there's the concept of sort of the B factor of this Gaussian, and adding some sort of inverse filter to sharpen it and squeeze it. We're not doing that at all. So we've done extensive tests on the amplified maps to make sure that what we're doing is not corresponding to a sharpening.
Thank you. That clears up my intuition about it very much more. So.
Yeah, no, I think we actually have it in the documentation where it says that the tool does not do sharpening. It tries not to.
Thank you. Despite the incoherence of the question, that was an awesome answer. All right. We have a question from Yu Yen. So let's see, are there plans to integrate or couple compositional heterogeneity to existing processing pipeline for the particle classification?
Yes, yes. This is one of the principal, like the origins of Occupy is in order to quantify things that we see in maps. But very quickly, it became extremely obvious that this level of intuition is something that should be transferred over to the processing software stack. It's a big sort of endeavor to do so in a systematic way. But there's simple ways that we've tried and they haven't worked. I think we understand why, and it's taught us something about how the processing programs work. But it's down the line, yes, it is happening, but it will take some time.
It does seem like the mathematical and algorithmic approaches for propagating backwards from three-dimensional to your particles, like there are lots of moving parts in there to be dealt with.
Absolutely, yes.
All right. Well, I think we've one last call for questions, and if not, then once again, thank you for presenting and for dealing with all the technical hurdles and medical hurdles.
Absolutely. No, it was a pleasure. Thank you.
Well, thank you. Have a good rest of your evening. And with that, I think we can call it closed.